We are diving into EMA, efficient multimodal understanding, generation, and editing with a unified architecture. A crucial new paper from Shin Hei and the team at Huawei.
Yeah, and this one really feels like a landmark moment in the unified multimodal space. If you're tracking models that try to do it all, understand, generate, edit EMA, it really shifts the
It
conversation.
moves it away from just brute force scaling, right?
Exactly. It moves it towards, architectural genius.
So let's get our key insight summary right out of the gate. We're talking about EMA, that's efficient multimodal understanding, generation, and editing a 4 billion parameter model.
And this 4B model is significantly outperforming the state-of-the-art 7 billion parameter models, like Bagel, across all the major benchmarks.
How does it do that? It seems to be all about radical token reduction.
It is. They use this incredibly efficient autoencoder that gets a massive 32x compression ratio. That's 4 times more compressive than a lot of its peers.
And the innovation just keeps going when they merge the visual inputs. So instead of the old way token-wise concatenation, which just, it blows up the sequence length.
Right. EMA uses channel-wise token concatenation.
And that single choice, that structural decision, reduces the number of visual tokens needed for a complex task like image editing by up to 5 times.
5 times. Compared to previous architectures, you combine that efficiency with a really sophisticated shared and decoupled network design, and then add in a unique mixture of expert strategy just for vision.
And what you get is a model that proves being architecturally smarter just beats being bigger.
That's why EMA4B is really setting a new foundation for unified AI.
Okay, let's unpack this victory for efficiency because it's a big deal. For the past few years, the race toward these unified multimodal foundation models has been really heating up.
Absolutely. Everyone recognizes that merging vision and language seamlessly is just critical for that next big leap, whether it's embodied AI or, eventually AGI.
And in this race, researchers have generally been following 3 main directions to get that unification.
Exactly, and EMA is positioned squarely in that first path. The unification of architecture formats.
Okay, so that's the direction that includes models like Bagel and Janus Flow. The goal there is deep end-to-end integration where understanding and generation are intertwined in a single network.
Right, where image-to-text, or I2T, and text-to-image, T2I, are all living together.
And the second path.
That's the unification of task formats. That's more like taking a pre-existing understanding model and just bolting on a generation decoder with some kind of bridge. Think of models like MetaQuery.
And the third path is unification of learning paradigms, using the same core optimization like a shared loss function across both tasks. Models like EMU3 had explored that.
But EMA's mission, their specific goal, was to solve the core problem that was plaguing that first architectural path.
Which was inefficiency.
Inefficiency, exactly. Those deeply integrated models, they always struggled with these ballooning token counts, which meant massive memory usage and really slow inference speeds. They had to manage the visual bandwidth without killing performance.
And that brings us right to their architectural pillars. And the first pillar is what makes everything else possible. Maximizing that efficiency by reducing tokens, starting with the compression ratio.
They use 2 separate, highly specialized visual encoders, but they're designed to work in tandem. First, you've got the understanding encoder, the undenk.
That one uses a modified SIGLI2. Its job is just extracting semantic meaning.
Right. And second, the generation encoder, or GenEnc, which uses a deep compression autoencoder, a DCAE, and that one's job is to preserve all the high-frequency visual details you need for diffusion.
And both of them are engineered for an incredible 32x compression ratio.
Using methods like patchifying and pixel shuffling. And to put that 7.2x compression into context for you, a massive 1024 by 1024 image gets compressed down to just 10,024 visual tokens.
I mean, 32x is just phenomenal. You almost wonder if they're throwing too much away, but the benchmarks prove they're not. And what's so critical is that this 32x is 4 times higher than the typical 8x you see in models like FLUX.
Which means EMA only needs a quarter of the visual tokens just for the generation side of things. It's a fundamentally cheaper, faster model right from the start.
That's the foundation.
That is the foundation. And because both the semantic encoder and the detail encoder share that exact same 32x compression ratio, it unlocks the second, even more innovative pillar, channel-wise fusion.
And this next part, this is really the most critical piece of their efficiency claim. How do you take those 2 compressed inputs and merge them into the LLM without, blowing up the token count all over again?
It really comes down to the difference between blending and stacking. If you look at older unified models, like Bagel, they relied on token-wise concatenation.
Which is like taking two documents, document A for semantics, document B for details, and just putting them end to end. Your sequence length doubles.
And the LLM has to process this huge number of tokens, which is super expensive computationally. Channel-wise, Fusion, on the other hand, is like overlaying those two documents.
Okay.
You blend the semantic and the detailed feature info along the channel dimension at every single token. The sequence length stays the same, but you double the depth of information the LLM gets for each token.
And that's where the big efficiency payoff comes from. That architectural choice is what lets MA reduce the visual tokens it needs by up to 5 times in tasks like image editing. It's an elegant solution to a huge problem.
Efficiency built right into the data stream. But the architecture still has to deal with that fundamental conflict. Understanding is about semantics, but generation needs semantics, plus all that high-frequency visual fidelity.
So they solved that tension with the shared and decoupled network design. Walk us through how that compromise works.
So the core idea is mutual improvement early on. The network is designed to be shared at the shallow layers.
Meaning both the understanding and generation branches learn common general features together.
Exactly. Features that apply whether you're describing an image or creating one.
But hold on, if they're sharing parameters in the shallow layers, doesn't that inherently compromise the generation side's ability to focus just on visual details? Isn't that the conflict that unification always struggles with?
That's where the decoupled part is so clever. The parameters become decoupled at the deeper layers. As the tasks get more specialized, say the generation branch needs to focus on pixel movement for an edit, the parameters split off to meet those very distinct needs.
So the network architecture itself is acting like a sophisticated filter, optimizing for 2 different outcomes at the same time.
Precisely. They even take it a step further. Even in those shared shallow layers, some components, like the value projection layers, are still task-specific. So even when they're learning together, they maintain the independence they need.
We should probably note the weights for both branches were initialized from Qwen 3.4b, which gives it a really powerful reasoning baseline.
Yep. And the optimization objectives are also distinct. Understanding tasks use the traditional next token prediction with causal masking. That makes sense for reasoning.
But the generation tasks use flow matching with velocity prediction. Why flow matching?
Flow matching is essential because it moves away from those traditional sequential steps. It makes the generation process way more efficient and deterministic than a standard diffusion model. That speed gain is absolutely key to Emma's whole efficiency claim.
So it avoids the long sampling chains you usually need.
Right. And for generation, they also use a hybrid attention strategy. This lets visual tokens attend to other visual tokens within the same image. So if you're editing a dog's face, the eyes and nose stay visually consistent with each other.
A kind of self-awareness for the image.
You could say that. It's a communication that just isn't necessary in a pure understanding task.
And to standardize it all, they apply 2D positional encoding to the visual tokens, then use the standard 1D rope E to process everything uniformly inside the LLM. It's a very clean approach.
So they've addressed token efficiency, they've addressed the task conflict, but then they decided to give the visual understanding side another specialized boost using a mixture of experts approach.
This is a great example of targeted efficiency, isn't it? Because multimodal understanding has to handle wildly different images. A technical diagram is not a photo of a cat.
A single general-purpose encoder will always struggle with that, so they extended their SIGLIPS2 understanding encoder into an MOE architecture. It's like having 2 specialists on call.
One specialist, a versatile expert, handles all the general photos.
But then they brought in a dedicated STEM expert: science, technology, engineering, and math. This expert only gets activated when the input looks like a complicated chart or a technical drawing, and a little router module makes that call.
So it stops the model from trying to process a complex graph through a general-purpose filter. What's the cost benefit here? The parameter increase must be tiny.
It is. Only about 50 million additional parameters. On a 4 billion parameter model, that's nothing. But that tiny increase improved understanding accuracy by an average of 4.4% across 11 different datasets.
High leverage research, minimal cost, measurable gain.
And it preserved all the generation and editing capabilities.
Okay, let's talk about the fuel for this machine. The data and training. MOA was trained end-to-end, integrating understanding, generation, and editing tasks all at once.
The scale is large, but it's manageable, which again speaks to the model's efficiency. We're talking 400 million I2T pre-training samples, 600 million for T2I. And for supervised fine-tuning, 12 million IT2I samples.
The training was staged, right? They gradually increased the complexity.
Yep. Started with pre-training at 512 by 512 resolution, then moved to fine-tuning where the understanding branch could handle native resolutions, and the generation branch went up to 1K.
And in that fine-tuning stage, they use a balanced sampling, eventually a 1-to-1-to-1 ratio between the three core tasks, so the model doesn't favor one skill over the others.
But there's one detail in their training that I think really shows their commitment to real-world utility over just chasing benchmarks.
Look at that.
Their exclusion of the GPT image edit 1.5M dataset.
That seems counterintuitive. Why would you reject a dataset that's known to boost image editing scores?
It was a principled choice. They found that using that specific dataset severely disrupts character consistency during edits. So while it might artificially inflate your GDIT score on a leaderboard,
it makes the model worse in practice.
Yeah.
So if you ask it to change a shirt color, it might forget what the person's face looked like.
Exactly. It sacrifices the subject's identity for a small numerical gain. This exclusion really highlights a limitation in the GDIT metric itself. It doesn't properly evaluate subject consistency.
That's a great point. That's the kind of decision that separates a truly useful model from just an academic curiosity. Okay, let's get to the results because this is where it all comes together.
On the understanding front, the changes immediately paid off. MA4B gets a 73.0 on MMVet. That's a huge lead over the larger Bagel 7B, which scored 67.2.
A 5.8% gain. That validates the whole approach right there.
And that STEM expert we talked about, that little MOE addition, helps Emma stay competitive even with specialized understanding-only models. It outperforms Qwen 3VL by an average of 0.4% across 11 datasets.
And what about generation, text to image?
Here, it's even more impressive. Emma hit at 0.91 on Geneval. And what's critical is it did this without using common boosts like prompt rewriting or reinforcement learning.
That is just massive leverage. For comparison, Bagel 7B hit 0.82 without those tricks. And Emma even beat the score of the much larger Qwen image that's a 20 billion parameter model, which scored 0.87.
Yeah, it's the first model documented to reach 0.91 on Geneval without those external techniques. It's just architectural smarts beating sheer scale.
On image editing, it's basically a tie with Bagel 7B, right?
Yeah.
6.53 on JIT versus 6.52.
It is, but here's the efficiency takeaway again. Emma achieved that state-of-the-art score using only 1/5 of the visual tokens compared to Bagel.
Which translates directly to faster edits and lower memory needs.
The paper wraps up by pointing out a couple of fascinating emergent capabilities, which really speak to the power of this unified end-to-end training.
Okay, like what?
First, cross-lingual transfer. MMA can natively support Chinese instructions for generation and editing.
Even though it was never specifically trained on Chinese T2I data.
Right. That knowledge transferred directly from the shared-understanding branch, which did see Chinese examples. The unification literally created a new capability.
And the second emergence sounds even more exciting for actual use cases. Complex instruction following.
Yeah, this is really cool. MMA showed it could follow multi-step editing instructions. Replace the cat with a dog wearing a blue hat, then put it on a spaceship.
Even though its training data was only single English instructions.
The thinking is that this comes from including multimodal chain of thought data in the overall training mix. It teaches the unified model how to sequence and comprehend complexity, letting it generalize far beyond what it was explicitly taught.
So what does this all mean for the researchers and engineers watching this space? To me, this paper is providing a clear roadmap.
I agree. We're seeing a distinct shift where smart architectural choices like that 32x compression and channel-wise fusion allow a smaller, faster 4B model to just dominate older, larger, less efficient unified models.
It means we're moving past the era where quality was just a function of parameter count.
The key to progress in unified multimodal systems isn't just scaling up the LLM anymore. It's about drastically reducing that visual bandwidth bottleneck. And Emma shows us exactly how to win that battle.
Which leads to a final, provocative thought for you to consider. Vision is the biggest, most expensive bottleneck in these architectures. Emma has just demonstrated a viable, highly efficient path to 32x token compression and a 5-fold token reduction. So, how quickly will this level of efficiency trickle down?
This efficiency leap is what unlocks the practical, pervasive future of unified AI. It could mean we see highly capable unified models running effectively on everyday consumer-grade hardware a lot sooner than we might think.